Hi, let me start my presentation. Today's presentation is about design of window cleaning robotic manipulator with compliant adaptation capability. I am Jooyoung Hong from Seoul National University, Korea. Before starting with the topic, let me brief shortly about facade cleaning robot M1, which is called FCR M1. As you can see in the pictures, this is a configuration of FCR M1. This is a prototype of facade cleaning robot which operates mounted on a gondola on a building. It consists of three big parts: a main body, which has cleaning solution storages and retrieved storage, 2 degree of freedom manipulator, which is a parallel manipulator, and a cleaning device. This parallel manipulator can adjust distance and angle between robot and facade. And a field test was conducted on a high-rise building in Seoul, Korea. As you can see in the video, the cleaning tasks are usually implemented along the gondola descending from the top of the building. When the robot meets obstacles like window frames while going down, the manipulator senses the obstacles and avoids them. And as you can see in the video, the gondola swings forward and backward when the robot meets the obstacles. After these experiments, there were some problems on the FCR M1. First, it is a large reaction force. As the robot meets the obstacles, the large impact force is applied to the robot, as you can see from the video and the graph. It causes swings of gondola, and this can lead to the unpredictable accidents. Also, there were large uncleaned zones near the obstacles. It is occurred because of the large height of the cleaning module and the path of the cleaning module as the manipulator detaching and attaching to the facade. From these problems, let me introduce next the prototype FCR M1C. There are two contributions in my research: downscaled cleaning module and optimization of 2 degrees of freedom SEA manipulator. By reducing the height of the previous cleaning module, it could increasing the cleanable zone, and it can overcome the obstacles passively with dry-star wheels. Also, by adding series elastic actuators, which is SEAs, in the previous manipulator, it could overcome the obstacles as you can see in the videos. This section is about a cleaning module. As you can see in the figures, cleaning module consists of squeegees, nozzles, brush, and suction parts. Squeegees wipes contaminated water. Nozzles spray cleaning solution. Brush sweeps decontamination, and suction parts suck in contaminations. As reducing the height from 330 meters to 83 millimeters, cleanable area increases as 75%. To verify the performance of the cleaning module, cleaning experiments are conducted on the test bench. As you can see in the video, window got dirty by dirt, and it shows apparently that the window is cleaned well compared compared to the pictures before cleaning. The next section is about optimization of manipulator. Optimization problem is set like this. The objective function is to minimize the change of reaction force at the target force during overcoming obstacles passively in workspace. The constraint functions workspace and dynamic equations are shown like this. The design parameters are R, L, B, K. R is a length of the wheel spoke. L and B are lengths of each links of the manipulator, and K is the spring constant. Optimization is performed analytically. As a result of the optimization, the average change of reaction force at the target force decreases as 43% from 7.04 Newton to 4.03 Newton. As you can see on the graphs, the lowest values are 113 mm with initial parameters and 125 mm with optimal parameters. With the optimal parameters, experiments are conducted on the test bench with obstacles. The experiments are conducted at 140 mm with 0 and 2 degrees respectively. This point, 140 mm, is the middle position in the workspace. As you can see in the videos, the ability of overcoming obstacles of robot is approved. As a result of the experiments, change of reaction force at the target force decreases as 47%, which is similar as the simulation result on the before slide. And at the point 125 mm, which is the lowest value in the simulation, the change reaction force is about 1 Newton. This shows that the reaction force is nearly unchanged at this point. In a nutshell, my research contributions are downsized cleaning model and optimization of 2 degrees of freedom SEA manipulator. By downsizing the cleaning model, cleanable area increases as 75%, and the cleaning performance is approved by experiment, as you can see in the video. And by optimizing 2 degrees of freedom SEA manipulator and adding the TriStar wheels, there's no need for switching control methods for avoiding obstacles during cleaning tasks, and the change of reaction force at the target force decreases as 47%. Also, springs and TriStar wheels reduce the shock and impact force on the robot, and the robot could overcome the obstacles passively. This is the end of my presentation, and thanks for watching and listening my presentation.